Okay, hey, it's HESSEL, coming at you with some extra practice in circular motion. So we're in brief review in physics. You should have the PDF on Google Classroom, and it's page 49 of the book, but that doesn't really matter. You just kind of start at the beginning with number 88. Again, to be clear, this is extra practice, so this is not the purple book or whatever color book we're using. But it's from a different book called Brief Review in Physics. All right, 88. So here's what we know. We know the mass is 2 kilograms. The cart, it's a cart. The cart's going counterclockwise at 6 meters per second at a constant speed. And then we know the radius of the circle is 3 meters. I drew the picture that goes along with it. And so 88 wants to know what is the magnitude and direction of the centripetal acceleration. Well, the formula for centripetal acceleration on page 6 of the reference table is v squared over r. Don't forget to square that speed. So 6 squared is 36 divided by 3 is 12. So 12 meters per second squared. And it's meters per second squared because those are always the units for acceleration. And then centripetal acceleration and centripetal force always point inwards towards the center of the circle. Inwards. Putting it towards D. So that's 88. Next, 89. 89 wins the centripetal force. Again, page 6 of the reference tables gives us the formula Fc equals MAC. And with our acceleration for number 88, multiply times the 2 kilograms of mass, we get 24 newtons for our centripetal force. All forces are in newtons. 90 wants to know what would happen to the centripetal force if you doubled the mass. Well, let's look at the formula for centripetal force. Fc equals MAC. You can see that centripetal force is directly proportional to the mass, so that gives us choice 2. Centripetal force doubles if mass doubles. 91 says if you double the radius, what happens to the centripetal force? Well, centripetal acceleration. Well, let's take a look at the formula for centripetal acceleration. Now for this formula, if you increase the radius, you decrease the centripetal acceleration because centripetal acceleration is inversely proportional to radius. As radius goes up, centripetal acceleration goes down. So if you were to double the radius, the centripetal acceleration would be halved. Choice 1. Now 92 wants to know what happens to centripetal force if you double the speed. And if you look at the formula for centripetal force, you might say, well, speed's not in that formula, so there's no effect. Now wait a second. Speed is in that formula. Remember the formula for centripetal acceleration. Centripetal acceleration is speed squared over the radius. When you combine those two guys together, you get that centripetal force is mv squared over the radius. Remember that that version of the centripetal force formula is not on the reference tables. The formulas that make Fc equals mv squared over r are on the reference tables on page 6. So just to be clear, I mean, it's not much of a stretch, but there you go. So we see that the centripetal force is directly proportional to speed squared. All right, so it's not just directly proportional to speed, it's directly proportional to speed squared. And they said double the speed. Leaving the mass and the radius alone, if we double the speed, since speed is squared, we wind up with 4 times the centripetal force. Double speed, 4 times the force. So the centripetal force would be quadrupled if you double the speed. 93 wants to know if you half the mass, what happens to the centripetal acceleration? Well, looking at the formula for centripetal acceleration, AC equals v squared over r, mass is not in that equation. So since there's no effect on centripetal acceleration, if you change the mass, the centripetal acceleration would, choice 3, remain the same. The force would be affected because F equals MAC, so M is in that equation, but the centripetal acceleration is not affected. All right, so 94 and 95 want to know direction. So 94 says, in the position shown with the cart on the right, pretty much at the 3 o'clock spot for the circle, towards which point is the centripetal force directed? So centripetal force we know points inwards. So in terms of points, inwards would be towards point D. And 95 wants the velocity, so the force always points inwards. The velocity always points forwards, tangent to the circle, perpendicular to the force. It's important to know which way the circle is turning, whether it's clockwise or counterclockwise. and this is a counterclockwise circle. If it was going clockwise, then the velocity would be straight forwards, tangent to the circle, at right angles to the force, but towards C, because the circle is going the other way. But this is counterclockwise, so for the position shown, the velocity would be towards A. All right, and 96 wants to know, which factor when doubled would it produce the greatest change in centripetal force? Well, let's look at the formula for centripetal force. So the questions are really asking if you increase mass, decrease radius, blah, 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 to saying which thing, when you mess with it, affects centripetal force the most. And really you would say, well, all things affect it equally, except we see that the velocity is squared. All right, that makes a big difference. So that whatever you do to the velocity, if you double it, it's actually quadruples the force. If you triple the velocity, it's 9 times the force. And as opposed to the mass or the radius, that is just, oh, double the mass, double the force, triple the mass, triple the force. So the fact that the velocity is squared means that the velocity has a bigger impact on the centripetal force than anything else. So which factor when doubled, or when anything, would produce the greatest change in the centripetal force? That would be the velocity or the speed, choice 3. All right, and that does it for 88 through 96, a whole column of problems. Let's take a look at 97. So 97 wants to know, as the time to make one lap around a circular track goes down, oops, I said goes up, hold on, down, then what happens to the centripetal acceleration? Well, looking at the formula for centripetal acceleration, on the face of it, time isn't obvious. You might be like, well, time's not in the formula, there's no effect. Now, wait a minute, time is in the formula. Time obviously affects the speed. If you can complete a circle in less time, you must be doing it faster, like v equals d over t, and this is constant speed, so I can refer to that formula. So as my time decreases, and that means a faster speed, and if I have a faster speed, I'm going to have a greater centripetal acceleration. So yeah, choice 2, centripetal acceleration increases if the time to complete a circle, which we call the period, decreases. So 98 is actually asking about the tangential acceleration of a cart moving in a circle. Tangential acceleration doesn't come up that often. That's because there is none. So yeah, tangential acceleration is the change in speed, the forward or back acceleration, and there is none. For uniform circular motion, there is no speed change. There's a direction change as you move in a circle, and that's what changes the velocity, but the speed itself does not change. So the tangential acceleration is 0, which is choice 1. Now there is an acceleration, like I said, there's a direction change, which changes the velocity, and that acceleration is the centripetal acceleration, v squared over r. That's not 0. But the change in speed, the tangential acceleration, is 0. All right, 99. So for 99, it says that the speed is constant and the radius, if it's a circular path, of course, the radius is constant. It says the mass is constant too, but that doesn't affect centripetal acceleration. And so if the speed and the radius are constant, then the magnitude of the centripetal acceleration will also be constant, remembering that magnitude means amount. Now, the direction, you could say that the direction is constant and that it always points inwards. That's not really what they mean by direction. They mean kind of like a cardinal direction, north, south, east, and west. And so actually the direction of the centripetal acceleration is actually constantly changing. Let me show you what I mean by that. So you have something moving in a circle, and if the acceleration is always pointing inwards, 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 inwards. So the centripetal acceleration always points inwards. But if we're talking north, south, east, and west, then the centripetal acceleration is always changing. Like at the top of the circle, then the centripetal acceleration would be pointed like south. Then at the 3 o'clock position, it would be pointing west. Then at the 6 o'clock position, it'd be pointing north. And then at the 9 o'clock position, it'd be pointing east. So in that sense, the direction of the acceleration is changing from a north, south, east, west perspective. So 99 is choice 3. All right, this page is running out of space. Let's start a new one. All right, so here's 100 through 103. Got a cart, another cart, moving in a circle at constant speed. So 100, which way is the velocity going? It's going, the circle is clockwise. So the velocity would be straight forwards, and that would be towards S. And then 101 says, which way does the centripetal acceleration point? And then for 101, that centripetal acceleration is inwards, so that would be towards point Q. So yeah, there's 101, the centripetal acceleration is inwards towards Q. I'm distracted. My daughter is bouncing around the house on a FaceTime with her friend, and so they're talking about what they got for Christmas. Anyway, and then for 102, mass has no effect on centripetal acceleration. We saw that in number 93. So if you double the mass, nothing happens to centripetal acceleration. Choice 1. 103, once the centripetal force, you do mv squared over r. And don't forget to square that speed. The speed is squared. And you wind up with 40 newtons. That's going to be choice 3. All right, that's it for that problem set, but we still have time left in the video, so let's move on. We're on page 63 of Brief Review in Physics. There's one question at the bottom right, it's number 32. We have a car going counterclockwise in a circle, and it says when the car gets to point A, if a passenger in the car threw a ball straight up, which way would the ball go? Well, we know that, like at the current position, the car is at the bottom, so the car's velocity is straight forwards. But then once the car gets to point A, the velocity will still be straight forwards. And so the ball in the car has the same velocity as everybody in the car. And so if the ball gets thrown up into the air, yeah, it's going to rise, but it still has forward velocity, same as the people. The people will stay in the car, and the car will stay in the circle because of friction between the tires and the road. But if the ball gets thrown straight up, it still has that forward velocity. So if the ball gets thrown, the ball's forward velocity goes forwards, not outwards. And so the ball would go towards C. And C is choice 3. All right, next. We have page 64, number 33. We have a ball moving in a clockwise circle. The ball is at the 9 o'clock position. And it says, which way does the velocity and acceleration point? Acceleration is inwards and the velocity is forwards. We've done that a few times already. That leaves us with choice 1. Next. 34. Ooh, symbolic algebra. Fun, fun. These problems always look intimidating because they don't use numbers, but we would do them the same way as if we did have numbers. So we have a satellite of mass m, and it's in a circular path of radius r, and it wants to know what is the speed. It said the centripetal force, of course, is Fc. They're using capital R for radius, whatever, and we're solving for speed. Well, we know that there's a formula that relates mass, radius, and centripetal force and speed. That formula is mv squared over r. And so they're using capital R. Why use capital R? Why don't you just use lowercase r? I don't know. They always like to make things like even just a little bit annoying. Just leave it as lowercase r. Whatever. All right, so we have S is mv squared over r, and we're solving for v. So we just need to get v by itself. So multiply both sides by r, and that gets rid of the r. Divide both sides by the mass. Again, we're trying to get v squared by itself. And let's square root both sides. We wind up with speed is radical FCR over m, and that is choice 1. Again, we didn't use numbers here, but we're still trying to get a variable by itself and trying to isolate it. And so we just did that algebraically without numbers. You follow the same process. All right, so here's page 68, numbers 88 to 93. We have a racetrack. Some portions are circular, some portions are straightaway. I have a 1,000 kilogram car. It's a car? It's a car. It's going counterclockwise around this track, and it's going 20 meters per second at a constant speed in the circles and on the straightaways, and it takes 20 seconds to go from C to D, which is not actually in a portion of a circle. So 88 wants to know the net force from A to B. And we can see from A to B, here's that segment right there, that is a straightaway. 88, if we were moving in a circle at constant speed, then the net force would be the centripetal force. But we're not moving in a circle going from A to B. It's a straightaway. So for constant speed and we're not in a circle, the net force is going to be 0. But then 89 wants to know what's the net force from B to C. From B to C, that's this segment right there, and that actually is in the portion of a circle. If we're in a circle, then the net force is the centripetal force. That's whenever we're moving in a circle at constant speed, the net force is the centripetal force. And we know centripetal force is mv squared over r. And for that portion, that circle, the larger circle, the radius is 100 meters. We have 1,000 times 20 squared over 100. And so 89, the net force is the centripetal force for 1,000 newtons. All right, let's do 90. And, oh, sheesh, I'm at the bottom. I don't have any more space. All right, I'm not redrawing that drawing. It's too much. But I'll have to start a new page and talk you through it. So C to D, 91 is the distance from C to D. C to D is a straightaway, and it's constant speed, so I can do V equals D over T. I know the speed, and I actually know the time from C to D. It told us that. It's 20 seconds. And so if we cross multiply and solve for D, 20 times 20 is 400 meters. 91 wants to compare the centripetal acceleration for the AD or DA curve to the centripetal acceleration for the BC curve. Well, it's all the same speed, but the radii are different. We know that centripetal acceleration is speed squared over the radius, but the speed is the same constant speed of 20 meters per second, but the radii are different. So the dA curve radius is 50 meters, and the BC curve radius is 100 meters. And so dA, it says compare dA to BC. dA has half the radius. And so dA has a smaller radius, and we can see that centripetal acceleration and radius are inversely proportional. And so that dA curve has half the radius at 50 meters, that's half of 100. So with half the radius that BC has, I see that radius and acceleration are inversely proportional. So at half the radius, it would have double the centripetal acceleration that the BC curve has. So 91 is double. 92 we can actually skip, but if you're wondering about the momentum, momentum is mv, mass times velocity or mass times speed, and with the same mass and the same speed, it's the same momentum, but we haven't done momentum yet. That's the next topic. Finally, 93 on this page. And 93 says if you put more passengers in the car, what does that do to centripetal acceleration? Nothing. More passengers adds mass, and mass does not affect centripetal acceleration. So you have more passengers, more mass, no effect on centripetal acceleration. Okay, and then the last set of problems in the Brief Review in Physics book actually deals with a lab that we're probably going to do. And then there are two more problems on top of that. So 171 through 180. So there's a lot of reading for this problem, but 171 basically boils down to that Tom says that they're measuring velocity, and then Julia says, no, we're not measuring velocity, we're measuring speed. And Julia's right. And the reason why you can measure speed, like for instance, speed, you can time the stopper going around so you can get the period. You could measure the radius of the circle. So you could get speed. Speed is 2 pi r over the period. You could time the stopper so you can get the period, and you can measure the radius. So you could calculate the speed. But the velocity, the actual direction of a moving stopper, yeah, since the velocity includes direction, if something's moving in a circle, its direction is constantly changing. So how can you measure that direction change? I can't really think of a way to do it. So yeah, you're measuring the speed there, not the velocity. So 172 wants to know how the number of washers attached to the bottom end of the string, as shown in the diagram, can be compared to the centripetal force. So let me explain how the apparatus works in terms of the string tension. So here's a little drawing of the apparatus. You got your glass tube, you have your string, which is attached on one end to the rubber stopper, which is moving in a circle at constant speed. And pulling on the other end of the string, you have your set of washers down here on the bottom. The weight of the washers pulls down on the string. And then if that rubber stopper weren't moving, then the washers would pull down on the string, and it would pull, the string would pull down, and then the rubber stopper would be pulled to the tube. But the rubber stopper is moving. It's moving in a circle, a uniform circular motion. And so that centripetal force is putting a tension on the string. So yeah, the tension in the string, it counterbalances the weight of the washers. And so if the speed increases for the stopper, then the tension is greater than the washers. and the washers move up. If the weight of the washers is too much, then the washers pulls down, and the washers go down, and the string gets shorter up by the circle. So yeah, basically the string tension provided by the centripetal force equals the weight of the washers, and the washers don't move up and they don't move down. If they're moving down, then there's not enough string tension provided by the centripetal force to counter the weight of the washers. If the washers are moving up, then the stopper is moving too fast, and the tension, which is providing the centripetal force, is greater than the weight of the washers, and it's pulling the washers up. So if those washers hang in place, if they don't move up and they don't move down, then the pulling force from the weight of the washers is perfectly countered by the tension in the string provided by the centripetal force. Now, what they can do, the question says, what's the relationship between the number of washers and the centripetal force? If you increase the number of washers, there's going to be more weight pulling down, and so you're going to need to increase the centripetal force in order to counter that. And if you hold the radius constant and just increase the speed, then you can achieve that. But that's essentially what they're getting at in number 172. So 173 wants the centripetal force in terms of the period, which sounds hard, but it's really not that tough. Follow along here. We know that centripetal force is mv squared over r. We also know that since in uniform circular motion, the object moves at constant speed, but the d in that case would be the circumference times the radius, and the time specifically is the period, the time for once around. So the short answer is that the centripetal force is the mass times, in parentheses, 2 pi r over period squared divided by the radius. But we can simplify that. All right, so I just kind of clean that up a little bit. I took the 2 pi r over t squared and just kind of set that aside, multiply times m over r. If I square everything in those parentheses, I get 4 pi squared r squared over period squared. The m over r, the r in the denominator, is canceling the square on r squared over here. So the question asks for FC in terms of m, r, and the period, and there you have it. FC is 4 pi squared m r over period squared. Again, I'm not sure that these are Regents problems per se. They're at the end of the book, so they're a little bit challenging, but they're still doable. 174, 2 pieces of equipment missing in their experiment list. Well, if they're going to be measuring the radius of the circle, they're going to need a meter stick. And it says essential, and they're probably right, but if you're going to have a whirling stopper, people are going to be whirling a rubber stopper on the end of a string, you should really have some safety glasses. 175 says that the two people, Julia and Tom, decided to measure the time for 30 revolutions instead of measuring the time for 1 revolution. And it said, why did they decide to do that? So 175, it says, why did they decide to do 30 instead of 1? It's hard to time once around. Imagine that you're whirling a rubber stopper over your head. To be able to time just 1 revolution, you're not going to be able to hit the stopwatch properly. So it makes a lot more sense to do 30 revolutions and then divide the time by 30 than to try and time 1 revolution. They're right in that taking 3 trials and then averaging them is good technique. It's just hard to measure 1 revolution. That's just not going to fly. Okay, so 176 says, it's kind of wordy, but basically they say, what should have been recorded when the pair was recording data? So all they need the radius of the circle. That would be the string length from the tube to the stopper. If they're going to do FC's mv squared over r, m is the mass of the thing in motion. They need the mass of the stopper. The key dependent variable that they're looking at here is the period of the revolution. How fast is the stopper moving, or how much time does it take to complete 1 cycle? So they're going to need that. And then finally, there's the washers on the other end pulling on the string. If they're adjusting the number of washers as their independent variable, then they're going to need to measure that mass. So 177 says, what would the graph look like for centripetal force versus the period of revolution? So in order to figure that out, we go back to the equation that we found before. And centripetal force is 4 pi squared times the mass times the radius over the period squared. We're holding the mass constant and the radius constant, so really it's just a function of centripetal force versus the period. So M and R are constant, as of course is 4 pi squared, that's constant as well. Our independent variable is actually the centripetal force, because that's going to equal the weight of the washers, and that's what we're adjusting is the number of washers. So that's the thing that we're changing, the independent variable, and what we're measuring, the period, as the dependent variable. So in the end, we have that the centripetal force is proportional to 1 over period squared. We've actually seen this graph before. We know that gravitational force from gm1m2 over r squared, gravitational force is proportional to 1 over r squared. And we know what that graph looks like. It follows that hyperbolic curve. And so the centripetal force versus the period in this case would follow the same curve. And there's our graph shape. So 178 said that Tom and Julia ran out of time and couldn't finish the lab. And I'm not surprised. They said they were going to do 4 to 36 washers in increments of 4. That's 8 trials. And then they're timing 30 revolutions around for 8 trials. That's going to take a while, even in a double period, especially if they needed to practice the technique. That'll take some time in order to do it. So yeah, I'm not surprised that they ran out of time. Speaking of running out of time, we're almost up to my 30-minute limit. There are 2 more problems on this page. Let's go. All right, so 179 and 180 is talking about a car turning in a curve. This is friction provides the centripetal force to turn through a curve. And 179 wants to know what would the coefficient of friction need to be in order to successfully achieve the curve? Well, we know that centripetal force is being provided by friction force. We know centripetal force is mv squared over r, and the friction force is mu times the normal force. We know normal force equals the weight. Interestingly, we don't need the mass. The mass cancels. Trying to get mu by itself. And there we have it. Mu is going to be about a half, 0.51. And finally, for 180, if the mass were increased, how would that affect the maximum speed at which it could round the curve? Actually, mass has no effect, and we determined that right up there where we canceled out the mass. The mv squared over r on the left side, and the mu fn, where fn equals the weight, on the right side. The 2 masses cancel, so mass actually has no effect. And that's it. Again, the problems in this book towards the end, like the final ones, especially that stopper, with the whirling stopper, with the tube and whatnot, the end problems tend to be harder. Those are maybe a little bit harder than what you could expect on the regions. I also said that we would be doing the lab in question, but not to that level of depth. We're not going to adjust the number of washers 8 times over. That's going to take forever. We're going to be doing a simpler version of that lab. But yeah, that's about it. So there's some extra practice for you. I hope it was helpful, and hit me up if you have any questions as usual. Thanks.